Hello, today continuation on the topic of complexity and performance of algorithms in general. So let's take logarithmic complexity and binary search in real examples. Let's get into it. First of all, I would like to slightly refactor this existing code so that it produces output like this and I don't have to manually change it. Should be easy to do. So here I will declare what kind of list counts I want to test. And we are performing test on this, and 400. Good. This we can remove. And wrap in a for each loop. List count. But also in the seeding method, since we will be reusing this class now, list clear. Everything is clear before seeding. Okay, and slight improvement to the output. Count, found count, and list. And list count. Right, build. Oops. And let's run it. And as we can see, we have basically the same numbers as we had here. And notably, the found count as well scales linearly. Right, so now binary search. So the idea of binary search is quite remarkable, but it can be applied only if some collection is sorted. So elements are in some order. If they are in order, then we can check the middle of the collection and see if the middle is bigger or smaller than the numbers that we are searching for, and then apply the same process now to the smaller collection. Basically, we can check now not the whole collection, but from the middle till the end of the collection, let's say, if the number that we are searching is bigger. And then we divide that piece into two and continue. And it turns out it is very fast. It gives us logarithmic complexity. We'll get into more details in the interview preparation. Here, we need to add ability to sort it. Well, let's say bool search. Let's keep a track of the value if it was sorted or not. And if it's not sorted, we would like to sort the collection. There are many sorting algorithms, but we can just use the built one for the list. And it is worth noting that sorting has to be efficient. If you try to sort with an algorithm that has complexity O big from n squared, then basically the whole sorting part will take so much time and squared that it might not even be worth to do it in the first place. Just search with queries. But this sorting, it's intro-sort and it's good. It has complexity of O big from n multiplied by logarithm n. Put it. This. Okay, so if it's not sorted, we need to sort it, but then search sorted. And we can use the built-in, again, list functionality for searching it. It has already the binary search for it. Note that there are many methods to find, but that's not what we are looking for, because they will give you O big from n complexity. We are actually interested is binary search. And let's see how we can use it. So index count item. What if we use the simplest one, just number, binary search for item, and it returns index. And we find an item if its index exists. I'm thinking, well, we can refactor it a bit later. Okay, so we have search sorted. Now going back to the test. Now, what we would like to do is to basically call search sorted here. Let's substitute search linear search binary. And yeah, let's run and see what happens. Okay, it was taking too long, it never ends. So I think there is a bug. Yes. Now, what happened? It sorts every time for every queries. I forgot to flip the flag. We actually need to sort only once, not for every query. Okay, now let's run again. Right, I got this results. Start next value here, that's fine. This is primary search. From here every time we multiply by list count, because no, not by list counts, but by query count. By query count. Let's put it this way. This is logarithm query count. But it's just because we actually have this loop, and if we need to find something, if we need to do 100 searches, it's just plain multiplier because the operations come. So we actually, for the sake of simplicity and brevity, abandon this. It should be O big from the count, and this should be from logarithm. Anyway, let's look at the results. First one, very quick, but then it didn't find anything. So this looks like a bug. Something is missing. Let's check. What could it be? Okay, one thing that I have found, index here is bigger or equal to 0. That still doesn't help. Need to search more. Why we can't find anything? What the heck? The list is getting cleared. We need to also flip false, sorted false. Right? This should work. Running. Oh yes. Oh yes. As you saw, basically instant. Time is basically neglectable, less than 30 milliseconds. Yeah. That's the power of binary search. Okay, let's refactor a bit more here. Yeah, first we can run a test with a million now, because previous one would take too long. Add a million. Let's see what happens. Yeah, it's still so fast. So you can see that when I increase twofold, let's see, 4 million. 4 million items in the list. It barely took 300 milliseconds. Let's actually do one more. 8 million. And I'm doing this because I want to show you an interesting correlation. $8 million. Yeah, this becomes very big. Can't find much more in it. Over time, if you pay attention to this, for 1 million it's 65 milliseconds. Then for 4 million it's 180. It's kind of 4 times bigger. From here to here, it's again kind of 2 times bigger. So that is because we have to sort the list, and sorting behaves in a n log n manner. So if we increase the size of the algorithm by 2 times, or if we increase the size of the collection by the factor of 2, it takes roughly 2 times more time to sort it. Okay, super fast, super speedy. Let's do one final thing. Let's refactor it, because I would like to bring more collections. I would like you to show hash set and how dictionary can be used, and how to actually use these approaches in real applications, because you won't be searching for the same number. So to do that, let's refactor this class. Complexity investigation. Basically, what we would like to have is a basic list of values. Let's extract an interface. In the interface, we would like to have 2 things. First is seeding, second one is searching. Let's click interface. Yeah, so ISearchable. And 2 methods. Seed and Now let's have it like this. Boolean is present. Value. Now we can have two implementers. Let's add this one will be binary search list. Binary search list. ISearchable. No, ISearchable. Implementation. And what we actually want. Here, let's add number and items election max value. That will be better. And just basically need all of this. Then the seeding will be like this for binary. Have this list. No, just count sounds better because it's not always list. Searching. Search. Value. Okay, this can be removed from here. This will comment out for now. Binary list. And let's run it, ensure that it works. Everything doesn't work. Something happened, right? Let's get back. That's because max list value was used. Here, max value. And run again. Now all works as it used to. Okay, so this is already a long one. Let's continue refactoring in the next one, and it will be useful because we'll add more collections to test, and this interface will help us to unify the testing efforts and to see what is the fastest way to search for data. Okay, thank you for watching, and I'll see you in the next one.